We've interpreted our problem and extracted all this information from it, so we're about ready to set up and solve our relative velocity equation here. But first, one more note on how to conceptually understand the differences between these three velocities. All velocities with respect to the ground, plane with respect to the ground, and air with respect to the ground, I think those are most easily understood. You can imagine that if you were just standing on the ground, watching the plane go by, this is the velocity of the plane you would see. And if you're standing on the ground, standing still, and feeling the wind blow by you, this would be the velocity of that wind. However, this one's a little more conceptually challenging, the velocity of the plane with respect to the air. So with respect to the air, from the air's point of view, what would you have to imagine here? I would suggest imagine something moving along with the air, like a little bit of dandelion fluff floating along with the air at the same speed as the wind. So from the point of view of that drifting dandelion puff, this would be the velocity of the plane. That's the velocity of the plane you would see if you were drifting along with the wind at the speed of the wind. Okay, well, let's set up our vector diagram to go along with this relative velocity equation. Okay, so far we've determined that the velocity of the plane with respect to the ground points due north, the direction the plane actually went, but the velocity of the plane with respect to the air was in this direction, 20 degrees east of north. That's the heading, so it had to point its nose in that direction in order for the plane to actually move due north. All right, so we just need our third velocity here, VAG. And let's see, we know that this was 600 kilometers per hour and this was 700 kilometers per hour in magnitude. So we can tell that this vector is longer than that vector. And that means that our missing velocity to close out that triangle there must be this. This would be the velocity of the air with respect to the ground. That way, we've got from our knowledge of how to add vectors in the head-to-tail method that VPA plus VAG, that chain of two vectors there, head-to-tail method means you make a chain of vectors, add all those up, and the sum points from the beginning of the chain to the end of the chain. So in this chain of vectors, VPA plus VAG, the sum points from the beginning of that chain to the end of that chain. So VPG, that's the sum of these two vectors. So we've got this vector diagram representing visually this equation for our relative velocities. Okay, so with this vector diagram, we can now solve for this wind velocity here by either doing some geometry or some algebra, or more likely a combination of both. I would recommend, if you've got a vector diagram like this, a sort of triangle that is a scalene triangle, then put it inside a big rectangle. Draw in some legs here to make this the hypotenuse of a big right triangle, and draw in a couple legs over here to make our blue vector also the hypotenuse of a right triangle. So make a big rectangle here and identify our lengths. 600 kilometers per hour, 700 kilometers per hour, 20 degrees right there. And I'm going to define this angle in here to be phi. That'll be the angle that indicates the direction that the wind is blowing. So we see that the wind must be blowing to the southwest in order to complete our diagram. So let's make sure that makes sense. So if we wanted to head due north, but the wind was blowing to the southwest, then if we pointed our head due north, the wind would blow us off course to the west, and we wouldn't end up right here where we want to be. So instead, since the wind is blowing southwest, we've got to kind of point our nose into the wind a bit, point it into the wind so that the wind blows against us, And that combination results in us actually moving due north. Drifting due north, that's what we want to do. Okay, so our picture here makes sense. Now let's go to a relative velocity equation. Since it's a vector equation, any vector equation is really represents multiple equations, one equation for the x direction and then one equation for the y direction. So the x component of the velocity of the plane with respect to the ground must equal the x component of the velocity of the plane with respect to the air plus the x component of the velocity of the air with respect to the ground. So that's our x direction equation, our I hat direction. And then in our j hat direction, our y direction, we've got the velocity of the plane with respect to the ground. The y component of that equals this y component plus that y component. So we must have separate equations for the x direction and y direction. And then refer to the geometry here in your diagram. The velocity of the plane with respect to the ground, the x component of that, well, that is pointing due north just in our y direction, so that x component is 0. The x component of the velocity of the plane with respect to the air, the x component of this, that would be this little leg, this bottom leg. So, okay, if this is 20 degrees here, then I can tell that this angle up here is also 20 degrees. So 700 sine of 20 degrees would give us this leg down there. So 700 kilometers per hour sine 20 degrees, that gives us VPA x, and that's pointing in the positive x direction. And then this is the unknown x component of the wind velocity that we're trying to solve for. Okay, so we can solve for that one. Then in the y direction, VPG y component, well, it's only pointing in the y direction, so that's our full 600 kilometers per hour there. And that equals our y component of VPA. So again, if this is 20 degrees, then this angle here is 20 degrees. So I want this leg of the green triangle. So that'll be 700 cosine 20 degrees. And that points in the positive y direction, plus the y component of our wind velocity, which would be, let's see, this little thing right here. That's the y component, and that's the x component of our wind velocity. So we're able to solve for those two components. Run the numbers, and we get these values. Note that they're both negative because our wind is pointing in the negative x direction and in the negative y direction. Okay, we're basically done. We've got our two components. Now just conclude by finding both the magnitude and the direction of the wind velocity. Note that in terms of significant figures, these intermediate results I have kept out to a large number of digits because they're not the final answer yet. I want to keep as many digits as possible until we get to the final answer. But then our final answer should reflect the significant digits that were given in the input measurements. And way back here in our input measurements, looks like we have one or two significant digits there. So we should keep probably one or two. I'll keep 2 significant digits in our final answer. So Pythagorean theorem to get the magnitude, round that off to 2 significant digits. And then to get the angle as well, we want the magnitude and the direction of our wind velocity. So I want to solve for this angle here, phi. I can see that tangent of phi is this over that. So solve then for that angle phi. We get about 14 degrees rounded off, and I'm calling it 14 degrees in this direction, south of west.